We are going to demonstrate the Networked Robots Enterprise application or platform that basically allows for multiple individual robots to be networked together, and where we can access each individual robot through a WebSocket API and establish a real-time connection to each robot. Now, each robot is running a program called the Remote Robotics Control Program. So RCP is implemented in a PIC32 embedded, written in C, running on an embedded processor. In this case, the system on a chip is a PIC32 MX360F512 from Microchip. So the platform and all the electronics in that regard is developed by Ionotronics. Every individual robot has the same processor running, and they have different Wi-Fi modules also developed by Ionotronics using USR series RS232T and also C210. And all robots are networked through a Wi-Fi access point, which we show over here. And the big box, the computer you see here is actually hosting the frontline Java server and the WebSocket multi-threaded server, which constitute together the Networked Robots platform and application running on Linux. Now, each robot has a RGB indicator which can show red, green, blue, and right now each individual robot is showing red. So let's go ahead and zoom in to the Rover here. There's a four-wheeled Rover, and you can see that the RGB is red. Okay, now moving over, we have a tank. And this tank uses 100-to-1 ratio geared Pululu motors with optical encoders, so we can also measure revolutions per second per motor, which is 2 in this case. You can see that it is red also. Let's go ahead and zoom in. And we have this one, which is also red. Okay, see that right there? And moving over, we got this nice little fella here, which is based on 4 mecanum wheels, and it is red. And going over here, we got a bunch of Rovers. Let's go ahead and take a look at this one. This one's red, and so is this one. Okay, so all the Rovers are showing red on their RGB. This means that there's no connection to the Networked Robots platform. In this case, the frontline server. So the frontline server is going to access a database table and then make a connection to each individual robot. So the database table has basically the 48-bit MAC address of each robot and its associated IP and port number, plus other information about the robot. So those are all stored in a nice table in a database implemented in MySQL on the Linux server here. And what's going to happen is we're going to start the frontline Java server application, and it will make connections to each robot, and then all the robots will be available for a Java application to connect to each one individually and control them all in one application, or you can have individual applications just controlling one at a time. Doesn't matter. You basically, because they're all networked, we can have one application that has visibility and control to all robots, so you can develop some pretty interesting and intelligent applications using multiple robots, in this case the Rovers, as shown. Okay, so now we're going to start the Java frontline server. And remember that all the robots are showing red, so they should turn to blinking blue when the frontline Java server connects to each one individually and starts sending the heartbeat. Okay, let's just zoom in real quick. So one more time, we see this is red, RGB is red, and red, Let's take a look at these robots over here. 3 of them. Red, red, and of course red over there. So now we're going to start the Java Frontline server, and as we start it, as you can see here, it'll make connections, accessing the database, connecting to all the robots. And let's go take a look at the robots. Zoom in, and you can see that the LEDs are all blinking blue. Each one is individually connected to the networked robots platform. Okay, let's go ahead and zoom in some more. So here we see the rover blinking, the tank blinking, also this tank blinking blue, all connected here and connected here. So all the robots are now on the networked robotics platform, connected through the Java Frontline server, which accesses each individual robot based on a table and a database in MySQL. And each individual robot has a unique 48-bit MAC address, and associated with that in the table is the IP, which the Frontline server uses to connect. So here we're going to show that each individual robot can be controlled through an HTML5 client. In this case, we're running the client on Chrome on a Windows 10 platform. So basically, we have the capability to serve the page in the JavaScript through a web page, or we can run it locally. We don't actually use any app at all. This is just basically Chrome opening up an HTML5 and Java with associated JavaScript. So this can be served from anywhere in the internet, and then you can control each individual robot through this simple client interface. And this client basically shows that with the WebSocket API and the Frontline server, we can connect to each individual robot and control it. So that's the purpose over here, what we're going to show. First of all, let's clear this, and we'll go click on this pull-down menu, and you can see all the robots basically with their MAC addresses. Let's take a look at that. And then a little description of what the robot is. Okay, so the first one is a tri-track robot, and we're going to select that one. And then, as you can see, first of all, I have to change this address because the actual Frontline Java server, the WebSocket server, is running on IP address 215, the port number, and we're just going to say connect. So we're going to make a connection basically through the HTML5 client running on Chrome to the WebSocket server that, you know, constitutes part of the networked robot platform with a Frontline server. So here we go. We connect, and we're going to send a message to the robot, which is Morse Code XX. And let's go take a look at that robot here. This is going to be this robot right over here. Let's go zoom in. It's a tri-track. Okay, and here we go. So on it we have a nice circuit that when we send Morse code, beeps, plays it out through a piezoelectric device, and you can hear the beep at around 2 to 3 kilohertz, and also a blue LED would flash indicating the Morse code. So we're going to send Morse code 2xxx's. Here we go. So we'll send a message. Okay, so you hear the Morse code. There we go. Let's go ahead and tell this guy to move forward. Okay, so we did that through this nice application we have. We have a form here which you can see, and we can actually tell the robot to go forward. Let's do an all stop, and we can tell it to go reverse or tank. So I'll be hitting these buttons here, and this is the speed we can adjust. This is all through the client. Now, since we can do this through a Chrome-based web page, HTML5, this clearly demonstrates that we can control all these robots using Java application or Python, or we can use Swift on iOS, on an iPhone and basically run the applications. Remember, because of the networked robots, we can actually have one application that has access to multiple robots. They can do combined operations with the robots, like make them run in formation, or basically do any application where each individual robot, we need access to each one to control them individually, so the combined operation will do something, like in a military application or a civilian application. So here we go. So basically, let's go back to the tri-track robot. Let's zoom in. Here we go. So you can see the tracks, and also there. And just for the heck of it, we'll send it a Morse code message, which is XX. And now we're going to tell it to go forward. Okay, look at the direction of the tracks. I'll tell it to stop, and then I'll tell it to go reverse. Tell it to stop and tank. Tell it to stop and tank in the other direction. Now this robot also has capability to measure the revolution per second per motor. You can see the two motors, and they have optical encoders, and we can access that information also. Okay, so now we've selected this particular MAC address, which belongs to a TS100 tank that uses Palula motors with the optical encoder 100:1 gear ratio, and we're connected. And what we're going to do is send a Morse code message. So first of all, let's go look at it. So I'm going to zoom into this guy right there. This is the one. You can see it's blinking. It's on the network. These guys have been on the network for about 3 hours. No loss of connection. And by the way, these are prototypes, so got all these clamps going on. Later we'll clean them up, clean up the wiring, make it look real nice. But for now, this is a prototype. Same goes for most of the other robots that you can see and we've dealt with before. So let's go ahead and we're looking at this guy, and let's go ahead and tell it to go forward through the HTML5 client running on Chrome. Again, let's send a Morse code, 2 X's. Okay, so let's tell it to go forward. And let's zoom in so you can see we have control of this robot as we had control of the other robots through the same client. Clearly showing that we can have control over multiple robots from a single application. And this gives it all the powerful applications in terms of combining all the robots to do interesting things in the combination, where an application has access to all the sensors and also can control each individual robot's motion, and, for example, monitor them with respect to each other, respect to the environment, and have an algorithm running which does interesting things. So you can see this is going forward. I'll tell it to stop. This is through the HTML5 client, and I'll tell it to go forward, reverse. Okay, this is actually forward, stop, reverse. You see that? And let's go ahead and stop and let's do some tanking. And they're going in opposite directions. Let's take a look at that. Here we go. Let's zoom in. You can see that. You can see the tracks are going in opposite directions. Okay, so I'm going to focus on this and tell it to stop. Now, I'm going to click. It immediately stops. And let's go the other way around. Uh-oh. Let's stop this guy. Go reverse. Forward. Counterclockwise. Clockwise. Okay, we've got to tighten up that track there a little bit. Okay, actually you put it on the ground, it's pretty fine. There you go, so we got that guy. Let's go ahead and see if we can control another robot. Let's take this guy. It's a tank with a wide frame. Take a look at this guy. You can see his LEDs blinking. So this is going to be very interesting. So let's go back to the application. Zoom out. And here what we're going to do is go back up. We'll clear this, disconnect, and select the TS100 tank with the wide platform, this guy. And you can see it's 48-bit MAC address, and we're going to connect to the WebSocket server, which is connected to the frontline TCP/IP server, and we have all the magic going on in terms of the code we've written in order to route everything and make sure the commands only go from the initiator to the particular rover or robot with the specified MAC address. Okay, so let's go ahead and send Morse code. And I'm going to go down here and let's get the tank started. So first of all, let me go back and zoom in. So this is the tank we're talking to. Okay, let's send the Morse code again. You can see the blue LED flashing when I send the Morse code. So that's 2 X's. And let's start motion. So this is going forward. Let's stop it. Go reverse. Stop it. Let's tank it. Tanking pretty fast. So that's one direction. We'll stop it and go the other direction. Okay. Full control over this robot. And I'm going to show how quickly we can go, for example, and connect to the rover. Send it this is the rover over here. And let's go ahead and tell it to go forward. Actually, that's reverse. Stop. Go forward. See? We can actually control multiple robots through the HTML5 client. Let's stop this guy and tell it to go tank. Of course, we've set the tanking to very high speed in these rovers. Okay. Let's do an alt stop. Now we got a little guy sitting in the corner there that needs some attention. So let's go ahead and control that one. So we'll pick that guy with its MAC address. Okay, let's go ahead. Take a look at that. There we go. So there we've selected it. We're going to disconnect the previous connection to the rover. Connect it to the, this is a rover with 4 mechanism wheels. Okay, let's send Morse code. Pretty loud little Morse code that little guy has. Alright, and then I'm going to start motion with this form here, and hopefully it doesn't roll off that platform. Let's go ahead and zoom in. Okay, so there's a guy, he's connected, he's got the blinking blue LED showing that it's connected to the frontline server. So let's go ahead and set it in motion. There we go, sort of jumped. Okay, so let's go the other direction. Okay, let's do some tanking. Pretty fast. Hopefully it doesn't roll off that platform. Okay, so this is one direction. Pay close attention to the direction. I'm going to stop it and then go in the other direction. Okay, let's do Morse code. You can see that nice blue LED blinking the Morse code and also the beeper. This is very good because We can send messages to the rover. Each Morse code message can mean something, and also the flashing blue LED is great because you can see it's getting a message. Okay, let's zoom out. Tell this guy to stop. Let's go in reverse direction. Let's go ahead and zoom in there. There we go. Let's stop this guy. Go the other direction. Forward. Okay, so let's go ahead and control this tri-track over here. So we got this tri-track in the corner. Needs some attention. And now this guy needs some calibration. It's got a little offset. So the track's rather moving even though it's stopped. So I'm just going to show you that I'm going to control that guy right through this browser here. So I've got it, and basically here we go. This is the MAC address, 48-bit MAC address right there, and we're going to disconnect from the previous connection, make a connection, send the Morse code, and then we'll do the motions through this web client. Okay, let's go with this guy, see what happens. First of all, let me zoom in. Okay, let's get the Morse code going. So we're sending XX one more time. Now I'm going to tell it to go start motion. So this is reverse. I'm going to stop it, go forward, stop it, tank, and stop it and go the other way. Okay. By the way, you can still send Morse code messages while it's moving. So let's do an all stop. Okay. Just for reference, this is the robot we started out with, which is tri-track. By the way, these guys have been pretty much connected for about 4 hours now. Let's go ahead and get that guy back up. Now I'm going to send a Morse code command. There we go. We should put that LED up front, so all our latest robot designs have that blue LED up front so we can see it, but you can hear the message. Okay, now I'm going to tell it to move reverse, stop, forward. Got it on slow speed. Let's go ahead and do some high-speed tanking, and the opposite direction. Okay, so you've seen that we were able to control every single robot here, and basically our network of robots has no limitation in terms of the number of robots we can attach, and in this case we have a Wi-Fi network, and we can also access these guys from anywhere in the internet, so through a tunnel. So basically, with this client, as we showed, which is HTML5, basically, we can just for experimentation purposes, with a simple front-end application, control any one of these robots from anywhere in the internet, and there you have it. Now, this page can be served from a website, and people can then try out these robots. We can put for example, you can put a video and basically show people that their commands are coming through and the robot is doing what they're commanding it to do. Okay, so this is very powerful. Again, this client here illustrates that we have a WebSocket API into our network of robots, and that WebSocket server does the heavy lifting in terms of all the routing. We have special code in the remote robot control program or command program, RRCP, which is unique, which makes sure that commands only go to that rover and responses come back only from that particular robot back to the initiating WebSocket client through the API. So, and obviously we can, as I'm pointing out, write a Java application that can access every single one of these and simultaneously have control over all of them to do combined operations, sort of like in a military operation where you're maneuvering a whole bunch of tanks and trucks and so forth. And but this is real physical, small scale, and have them do combined operations and basically monitor all the sensors, RPM, gyro, accelerometer, etc., and make it do interesting things. Now, the rover and the where I'm going to zoom into right here is uses 4 mechanism wheels. So we're building, we've already built up robots that take advantage of that, and we can control each individual wheel, and these are mechanism wheels so that this rover can go sideways, diagonal, forward, reverse, tank, clockwise, counterclockwise. So this guy can maneuver through a maze, and we're in the process of building 10 of these, and we're doing that professionally with laser cutters, laser printers, and so forth. Great layout. Those are coming up, and the plan is to, for example, we'll have say 10 of these rovers. We'll just put them on the ground, and what we'll do is using the magnetometer sensor, write a Java program that interacts with all of them simultaneously and aligns them with the North Pole. Also, they're going to have 4 ultrasonic sensors, 2 on each side and front and back, so they can maneuver through a maze or align themselves with other rovers and move in a coordinated fashion toward a target, say a wall. Okay, lots of opportunities for writing code. And we prefer Java, obviously, but it can be written in Python, no problem, or C, C++, doesn't matter. But Java is very powerful industrial strength. And we also have a demonstration of controlling these rovers with a joystick. And that joystick application is actually proving out that we have 2 entities that can communicate with each other through the network of robots, basically through our WebSocket API and our frontline Java server, because basically the joystick is connected to the same platform that controls the robots. We're reading the potentiometers of the joystick through an I2C device that we've developed electronics. Gives us 4-channel ADC. We also have fire button. And basically we take readings off the joystick. It's connected to the frontline server, and then route those movement commands to the rover. So we're going to build up 10 joystick consoles. They're all on the same network. They all have the same platform. They're all running the same RCP program. So that's very interesting, symmetrical in that sense, scalable. And we can have, 10 people simultaneously controlling 10 of these rovers. And we can also have applications where coders can use the network of robots to write complicated code algorithms that use a combined number of robots to do interesting things, way more interesting than the swarms, because now you have full access to all their sensors in each individual robot, and you can put a pretty sophisticated program to accomplish a certain mission. And the applications are endless. Okay? Now we have separate videos that show these rovers basically on the ground doing tanking, moving forward, backwards, sideways, etc. And those are coming up. But hopefully we've illustrated the power of our network of robots with which have the frontline TCP/IP server and the WebSocket, multi-threaded WebSocket server that does a lot of the routing. And the frontline gets all the information it needs about each individual robot from a database table, from a MySQL table, all running on Linux, all MySQL freely available. Of course, Java is available from the Eclipse Foundation, 64-bit, no problem. And with that, we'll end the discussion. There's going to be a whole series of videos following this one showing various applications. All right. Of course, one thing we want to point out is that each robot is connected to its own power supply. These are power supplies where we can current limit, and we're showing the voltage at the top. In the middle is the consumed current, and that's the power in watts. Now, for example, let's take the Rover in the corner here and look at its readings, which is 12 volts running idle at 0.263 amps. And what I'm going to do is get that guy moving full speed ahead, tanking, and let's go ahead and look at the current consumption. Okay, just to be sure, let's send a Morse code message. There we go. Now let's look at the power supply, and I'm going to tell it to tank. Okay, so you can see it's tanking very fast, and the current went up to about 1.1 amp. So this is very good in all the robotics applications, is that you have a bench set up first to verify all your algorithms, okay, and then make sure the power supplies are current limited. So you can make sure if things go sideways, you can limit the current and shut it all down. Also, it's very important to be able to monitor the current in wattage and relate that to the mechanical movement in terms of the increase in power consumption based on obviously the mechanical movement here. And as we know, for example, current is related to torque, and although this is a bench test, but this is good to know before you set it on the ground. In that case, you have a battery and you won't be able to monitor the current, but we have ways to do that too. Okay, so what I'm going to do is zoom into the power supply, and I'm going to stop the rover through the client. And the current dropped to, there you go, 0.26 amps, 0.268. Now let's go ahead and do a slow forward motion. Let's get reverse motion. And you can see the current went up a little bit to 0.7 amps. So a lot of good experimentation with these power supplies. I highly recommend that each robot be controlled with its own power supply like we're doing in a laboratory environment. Of course, when you're testing out the networking and the link between each robot, this is very useful to have this lab bench set up before you set them all on the ground and work out all the issues. Now, by the way, each one of these robots is configured so that if it loses that heartbeat, it'll stop. So if it's out of range and you can't control it with a joystick or something, it'll stop. And basically, when you bring it back in range, it'll get reconnected again. Okay, so that's very important. All right, so I thought very important to point out the laboratory environment and how important it is to start out by driving these guys with these power supplies. Now these are rock seat power supplies, and we recommend the 30 volt 10 amp version. And although we got 65 volt 5 amp versions too, but the recommend the 30 volt 10 amp. These are switching power supplies, so they're pretty light. And of course, we're not doing any RF or anything like that where signal noise ratio is critical. So the switching power supply is fine. Otherwise, we use the corettes for the RF work. So here we go. We see the other bench power supplies. Over here, let's go ahead and zoom in. Let's see here. Bricks are blocking it, but there you go. 3 power supplies for these 2 Rovers, and the Rover and the left of the McKinnon Rover. Okay. Very important to set this up in a lab environment like this to work out all the networking problems, and do a lot of work on the algorithms, especially in terms of measuring the sensors. And then of course you can put them on the ground with a battery and test them there too. Good to have some people in the room to stop the Rover if it, because you're writing code, if it does anything funny. Okay, based on experience. Okay, because it's code. You're writing code, you're developing code. All right, that does it. Thanks.